So in this video, we're going to be talking about the general steps you can take to solve a whole circuit. For the most part, it looks like there's a lot of different techniques that we have, but in reality, the techniques you choose are just those that make it easier to follow these steps. In this entire video series, we'll be talking about those different techniques and when to know when to use which one. But before we can do that, it's very important to understand what exactly it is we're trying to do. In the very beginning of this video, what I'm going to be talking about is the idea of solving a whole circuit. Later on in this video series, we'll talk about when we're asked to solve for a specific thing, because typically that might make the problem either easier or harder, depending on what we're being asked to do. However, if you can solve a whole circuit using a set of techniques, then you can use those techniques and modify them to solve for particular things. And that's why it makes sense to start with solving a whole circuit. But before we can do that, what exactly is it that we mean when we say solving a circuit? Well, to solve a circuit means to find all unknown currents I, voltages V, through every element. Now, I say through every element. Normally we'll have resistors and sources, current sources, voltage sources, various dependent sources. In the future, we'll also talk about things like inductors and capacitors. For the most part, in this course and at this stage, we're only really interested in the currents and voltages through the resistors. Unless otherwise specified, once we've solved for these, we're typically done the question. If that isn't the case, then you need to use these same techniques to do everything for the sources. But for now, let's assume that for the most part, unless it's needed to solve for the resistor current and voltage, really we're just looking for the resistors. So what are the steps that we're going to take? I'll outline the steps and then outline why we're doing them. The first step is inspection. In the inspection step, we want to write down every variable we can see directly. And that's every variable. Now, what do I mean by directly? I mean without computation. Any calculation or computation at all. In other words, if you can look at the current, for example, through a resistor and say it's 2 amps, then you have done it by inspection. On the other hand, if you need to use Ohm's law to solve for that current, you cannot do it by inspection. Doing something by inspection is important, even if you feel that looking at the circuit it should be obvious. The reason is because if you're looking at the circuit, it might not be as clear, depending on how the circuit is drawn, what all the variables are. So being systematic in your variables, being systematic by writing them all down and putting as many numbers as you can down before you begin solving the circuit, will help considerably. The second step is to identify series and parallel connections. What we're doing here is we're relating variables together. Remember, series means we share a current. Parallel means we share voltage. The benefit of this is if we have two elements in series, well, we can just say I1 must equal to I2 because they're in series. Similarly, if they're in parallel, V1 could be equal to V2. We'll be doing an example with a real circuit in later videos. Step 3. What I might call the one equation variables. I'll use the shorthand EQ'(n) to mean equation. What is a one equation variable? Something that can be solved for using only a single equation, for example, Ohm's law. So let's give this a little bit less abstraction. Here's a resistor that is 1 ohm. And let's say that I know that the voltage across it is 10 volts. Using Ohm's law, I'll know the current is 10 over 1, or 10 amps. I used only a single equation. I didn't need to bring in additional things from different variables. Using one equation variables, we can now start to actually solve for these series and parallel variables, assuming that we know them. Our next step is to form the equations. And this is done using things like KVL and KCL. What we're doing is setting up the equations that we're eventually going to solve. Ideally, these will give rise to more one-equation answers. But usually that isn't the case. Normally, Ohm's law, when dealing with resistors, is really the only one-equation answer you're going to be able to find. So now we have a set of equations. We form them into a system of equations. Now, the system of equations is where we almost always will be ending up. What you want to make sure you do is have as simple a system of equations as you can. In this case, I can define the word simple to mean fewest variables. Essentially, the smaller the system is, the easier it will be to solve. So, what is the common feature of all of these steps? We begin with a large set of variables. Through various techniques of progressively increasing complexity, we reduce the number of variables. We begin by inspection. No computation. This allows us to list the variables. We go into series and parallel, giving rise to one-equations variables. You may have heard this called plug and chug. What it means is you have an equation, and all you need to do is plug all the variables into it, and you will get other variables back out again. Finally, we have a system of equations. If we've gone through these two steps here, then our system of equations will have the littlest number of variables possible. It'll therefore be easier to solve. How do we set up that system? In this course, you can always begin by nodal analysis. Nodal analysis is a very powerful general technique. It might not give you the final system of equations. It might not be enough. However, starting with nodal will certainly give you a significant number of the equations you need. If you have n equations and you end up with n unknowns, you're okay. You can solve, and nodal was sufficient. If not, you need to go back to all of the relationships between the variables that you found. And generate your extra equations. Now, these are the general steps and why we're doing them. In the next series of videos, we'll be going through each of these steps for a real circuit and showing how they can reduce the number of variables and simplify my system of equations. Once we're done with that, we'll look at more complex examples where, for example, it's not obvious where things are in series or in parallel. With those examples, we're going to have to use additional techniques to look at the question and ask ourselves, how can we reduce the number of unknowns? However, if we can't reduce the number of unknowns for circuits where things are laid out in a more straightforward way, then we certainly can't do it when things get more complex. As a result, we're going to stick to a circuit that is laid out in a way where every single one of these steps is hopefully clear to you.